Hey everybody, this is Larry. This is me going Q4 of the weekly contest 441. Count beautiful numbers. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So this one, honestly, it took me a little bit of time to kind of figure it out. I think the hard part about this was that is the complexity analysis. So honestly, I did not know. I think the reason, so the reason why I did this with what people call digit DP is because honestly I didn't know how to do it. Right. The reason why I did it this way is because if it didn't work, I would just have no answer. So basically, this is my one and only idea that I had, and because it was one and only idea that I had, like I said, if I didn't do it this way and it didn't work, I don't know if I would know how to do it. At least without putting in a lot more time. But this was basically my first instinct. The reason is also because the constraints are 10 to the 9, so it becomes like, well, like, yeah, 10 to the 9, so yeah, you cannot brute force it, obviously. Okay, so the first thing that you have to do, and this comes up a lot, which I don't really like, but it is what it is, and it's just like a very small trick. Once you know it, it's not that bad, but I don't know. So it's not really that interesting if you ask me. But basically to get it numbers in a range, keeping in mind that for this problem, you can think about this. There's a couple of ways to think about this. And hang on, I'm putting up the drawing board. Okay. So the way to think about that I think about this is that okay, so you have these binary things, right? In terms of whether a number is a beautiful number or not, right? So basically, for example, you may think of it as some function, right? Some function. So is one a beautiful number? Yes. So that just return one for it is. 2 is equal to 1 dot dot dot, right? And maybe f of 11 is equal to 0 because it's not, right? Okay. And so here, if you want to write this out as an array, you can think of this as like 1 1 1 1 1 1 1, right? Dot 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 dot, maybe some zeros, some ones, dot dot dot, right? And then now the idea is just to get a prefix sum, right? So if you now aggregated this around, then now you have 1 2 3 4 dot dot dot, right? Regular prefix sum stuff. So then now the idea here is that if you are trying to get a range of numbers, say from, I don't know, 10 to I don't know, 900, right? Then it is just you go from 0 to 900 subtracted from 0 to 9, right? Which 9 is 10 minus 1, because then now, if we just think about it just in prefix sum or segments, maybe 900 is a little bit too big, honestly. Maybe that was a mistake. But let's say you have a number line that looks kind of like this, and then you're looking to figure out this is the left, this is the right, right? So this is the segment of thing that you're looking at, and this is just 1 0, some binary things, right? Well, that's just equal to this binary thing. Pretend it's a straight line from 0 to r, subtracted by left. I mean, these are discrete numbers, so you have to be a little bit precise. So L minus 1, right? The numbers that are to the left of this. So basically from that's how you get from L to R inclusively, right? Okay, so that part is fine. And then the second part, so from that, right? So if I look at the code, this is where I get the return f of r minus f of r minus 1. So that gets rid of the range. And in terms of complexity, it really matters, right? Like maybe there are different ways to do the DP without it, with the digit DP. I used to be able to do a digit DP that actually bounds this more, that does both the upper and the lower at the same time. But I think now, honestly, it's needlessly complex. And it probably does the same thing anyway, it's just in a different way. And the idea here, of course, is just that because you're calling the function twice, that's it, right? So whatever the complexity is, usually if you double it, it's going to be fine. If it's not, then you have other issues anyway, frankly, at least for this, right? This kind of idea. Anyway, okay, so now the digit DP. I'm not going to lie, a lot of people have a template for digit DP. And this idea of filling it out, I never do. I don't know. Maybe I'll be a little bit faster if I did, to be honest, because it took me 26 minutes. So yes, I'm not DP. I can almost always solve, but I'm always kind of slow. And the way that I do it is just by case analysis, to be frank, and we'll go over it together. My code is awkward looking and weird, and maybe I don't even recommend you to copy it, but I just want to express like the idea. The things that are important to me are the ideas and being able to solve it. It'll be also be better if I'm able to solve it faster and cleaner and all these things. But I just want to focus on solving it and so that I don't have to remember stuff, right? It's just about having the idea. And once you have these approaches, then it translates to more difficult problems, because on more difficult problems, maybe maybe it doesn't match your pattern anymore, and then you don't know how to do it anymore, right? And you have to actually solve the problem instead of pattern matching, right? That's how I kind of think about it. And for me, for digit DP, it's just case analysis as a result. So we'll go over it. So now we have f of x. What does it mean? I think I don't need this, but I think I just did it for funsies. If x is equal to 0, we just return 0. I mean, basic base case. I mean, it's not even a base case because we only call this twice. Otherwise, I convert it to a string. It's not really necessary. It's just easier for me to kind of do two things. One is converting it to a length, right? Meaning the number of digits in this number, and then also I'm able to iterate on it. And this looks very intimidating. I promise I'll go over it. But yeah, so let's say we have length. We'll go over it in a case. So let's say we have length 5, right? The code is in a way such that things can call each other. So we're going to start from here on line 35. So let's just, for example, if L is 5, what does that mean? That means that we have a 5-digit number. So what we want to do is just calculate the total of, well, we start with 1 digit. Well, technically we start with 0 digit, but calculate total will just return 0, I think. But yeah, so here we go. Okay. So let's say L is 5, so we have a 5-digit number. It doesn't matter what the 5-digit number is. Then now we calculate, okay, we want to get count of all numbers of length 1, 2, 3, and 4. Not 5, because 5 is a special case, because it matters what the number is. But 1, 2, 3, and 4, we don't have to worry about it, because we just want the total of all those numbers, right? Because it, from 1 digit it goes to 0 to 9, and obviously that's going to be, all the numbers are smaller. From 2 digits is 10 to 99, and all that number is going to be smaller, so we just calculate that, right? Okay, so how do we calculate this? So we have this thing. Honestly, I cached this, but I don't think I need to, because I don't know. But anyway, it's easy to just add a cache on things, and there's only at most 10 digits, so you're not really using that much memory anyway. So yeah, anyway. But yeah, for that, I have total is equal to 0, and then I have this function to help me. I'll go over it in a sec, but basically this just gives me all the count for all the numbers of length L. Yeah. And then this is the case that is a little bit tricky, but we'll go over here, right? So here, and this caused this thing, which we'll go over now, but it gets the count of all numbers of length left to go, right? Meaning that, okay, you still have left number of digits to resolve. This is the current total. This is the current product of the digits that we already did. And yeah, and then we try to get the number of counts, right? So how do I do this? I'm not going to analyze this complexity yet. As I said earlier on, honestly, my YOLO for this one is that if this didn't work, I don't have another solution. So that's why I did it. So it's not a great reason, but it's a starting reason. I thought maybe there's some parts I can optimize if I have to, but I didn't think so. But I wasn't sure that it was going to work 100%, but I was hoping. The other thing is that I know that product. So I guess I'll go over complexity a little bit first. Total is just, well, there are 10 digits, right? Or 9 digits? Yeah, we have 9 digits. They all go from 0 to 9, so that's going to be 9 times 9 to 81 in terms of the sum. That's fine. Right? Product, however, each of these could be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's 9 digits. So is it 9 to the 9? Right? So that's the thing. So that's obviously going to be a huge number. Oh, sorry, this is not 9 times 9. This is 9 to the 9 power, right? And so my guess, well, what I was hoping for anyway, is that the number of unique product is small. That's really the short answer, right? Because for example, if you have 1 0 in all the number, then the product is going to be 0 no matter what, right? So, and if the product is 0, then it, like, that already eliminates a lot of possible products, because it doesn't matter what the rest of the numbers are, it's just 0 if you have 1 0. So kind of like that. I mean, it's not enough of a proof, right? I'm not trying to prove yet, but that was enough for me to go, okay, let's try this kind of thing, right? Just to be full disclosure. So that's why like I said, it's not good. It is good enough for me to try, right? And left, of course, just goes to 10 because that's 10 digits or 9 digits or whatever, right? So yeah, so that part I'm not worried about. So I was just hoping that this is going to be fast enough. And then I just did the case analysis, right? So if left is less than 0 for some reason, I probably just have like weird places where I have, I don't know. Then we just return 0. If left is equal to 0, then now we can do the rule that they told us, which is with product mod total is equal to 0. Then we have one number that's true. Otherwise, we return 0. Yeah, and this is a shortcut that I did, which is that with product is equal to 0, then the answer is always going to be true, because 0 mod anything is, except for 0, I suppose, is always going to be true. And so then this is just the power of 10, because the rest of the digits could be all 0 to 9, so that's 10 numbers per digits left, so it's just going to be 10 to the power of left digits. I don't know that this is necessary, honestly, but it's still very nice, so I just kind of added on, because so then I don't have to worry about it or thinking about it. Yeah, and then otherwise this is just straightforward dynamic programming, right? T is equal to 0 for each number, keeping in mind that the first digit is always set for us, because here, for example, maybe I didn't go over this actually. This is the first digit, right? And if for length L, the first digit has to be 0. Has to be not 0, right? So that's why we start from 1 to 10. Technically 1 to 9 inclusive, the 10 is exclusive, right? And then the product and the sum is all going to start at I, and we start with L minus 1. So in this, but on the second digit on, it goes from 0 to 10. And yeah, I mean, this is just updating the states. We used one of the digits. We do total plus I, product plus I, and yeah, and that's it. Yeah, that is it. I think one thing that I'm just realizing right now is that this does not need to be inside. We'll explain that in a second, but yeah, so just to also kind of check out the complexity really quick. I do want to try a few things with complexity, that's why I want to bring it up. And will be easy to bring up if Leetcode wants to load them. But anyway, let's finish explaining this part, right? So okay, so now what we should understand is that how to get all the count of digits where the number of digits is fewer, right? So if you have 5 digits, say I was 0 to 5, we calculate for 1, 2, 3, and 4, but not 5, right? So for that case, this is an idea that I have similarly, right? Which is that, yeah, I go, okay, so the way that I think about it is that, okay, so for the first digit, let's say the first digit, we'll do a case, right? So let's say the number that we're caring about is this number, right? Then now the first digit, we always try, with this, what we did is that we tried all the numbers where, 1 digit, 2 digit, 3 digit, 4 digits, and 5 digits, right? So now we have to try the 6th digit in this case. And then, well, how do I do that? Well, one is that we just brute force the first number, right? So we know that we have 1. And then if we have 1, then the rest of the digits don't matter. So that's how I did it. 2 digits, the rest of the numbers don't matter, right? And, but 5 it does, right? So here, this is what we do, right?
And so that's what basically this loop does, is that for the first number, and this looks a little bit wonky because we want to have an exception for the first number, because the first number cannot be 0. After that, it can be 0. So yeah. But here we just go, okay, well, and I PP for prefix product and prefix sum. We'll go over what that means in a second after the first digit. But for the first digit, then now we go, okay, well, 5, yeah, we have to kind of take care of it. So yeah, right? You cannot just do all of these. So then now with 5, we're okay. But then now we have to do the next digit, right? So here, you may think of it as this way, right? Maybe just here, right? And what that means is that now we brute force. Now we can have 0 because it's the second digit. And then now everything, we consider everything, right? And then 5, 1, we consider everything. 5, 2, we consider everything. 5, 3, well, 5, 3 is we care about, again, the rest of the digits. So now we have a placeholder. And then that's basically what this loop does, right? Is that here, it just tries every number up to that digit. And then here, it sets the prefix up from the previous state to kind of go from 5 to 53, for example, and then now we try, what is this number, 531. So then we try 530 xxx, right? 531, and then here is the prefix, so it cannot be xxx. So then now we do this, and we have a underscore thing, and then now we try the same with 0xx, 531, 1xx, right? And all these states we kind of already. That's what this thing does, is that we just keep track of the prefix plus the I, right? So all that does is just, for this, we keep track of the sum and the product. Well, this is maybe a little bit trivial. And this is the sum of and the product. And then we just call the function that we already have, which allows us to get the core, the product, and the number of digits left, and get the total from that. And that's it. So that's all this thing does, is this getting the first digit, getting the rest of the prefix digits, right? And of course, here is the n, which is if you match the number exactly, 531613. Then if this is if this mod is equal to 0, then we increment by 1, because then now that exact number has 1 entry, and that's it. Yeah. So that's basically the idea behind this 1-digit DP, and yeah, the complexity is kind of wonky, right? Like, you have a lot of O of L's, O of L's, I guess just 2, and this is O of L times, I don't know, 9 if you have to, because if these are all 9s, then this is going to be just L times 9. Also, like, that's like 10 squared, not that many digits. So everything is just going to be based on this complexity. And honestly, like I said, I don't know, but there are some bounds you can check. Not this one. Oh, wait. Oh no, this is going to be loading again. I was hoping to play around the complexity. But yeah, we'll still play around the complexity. But yeah, so there are a couple of things that I was thinking of, and this is, if you watch the live portion of this, like after I submitted this, I actually was trying to work this out. I go, okay, well, how did I figure this out? I think for me, the most important thing is not necessarily getting the exact number, but it's that to get an order of magnitude, so that for future problems, if I have similar things, I have a better intuition. And I was thinking about, like, with some comments about like bars and stripes and stuff like this, because I noticed because for here, I go, okay, well, if there's only 1 digit, we have 9 digits to choose from, and there's only one of them, or we choose one of them, so it's 9 choose 1. If there are 2 digits, then it's either both those digits are the same, or both digits are different. So and there's 9 choose 1 of them and 9 choose 2 of them, right? Technically, maybe this is, yeah, I mean, in terms of unique products, right? So the order doesn't matter for unique products. And I'm trying to get an upper bound, right? So then you have like this thing, and this thing, and then as you realize, then there's this like Pascal triangle thing, but that's, and which reduced this to like the bars and, bars and stripes, or whatever. But except that these bars and stripes don't take account the unique 9-digitness, right? So because this has to times by 9, because that's just all the same number. This is for 5 digits, it means that 1 digit is, and then you have 4 digit that are a different number thing, right? And it also goes, you know, and all of these, that's this times 9 choose 2, right, and so forth, and dot dot dot. So, but that said, that's interesting and all, but I couldn't figure out what that means in terms of like a tighter bound. And here I actually, and you can watch this. I have this on the live portion. Is that I actually implemented the DP, a similar DP of just getting all the product and then putting them on scene, so that I get a unique thing. And the reason why I cache this is just so that basically we see, because I don't even have a return value, so the cache just makes sure that if we have we see PN left again, we don't call it again, so that because all we care about is this unique, and we already seen PN left, then we're not going to see a new answer to this, right? So that's why. But yeah, this is just every product from 0 to I, and actually 0 shouldn't even matter that much, but it's for completeness, right? For the first digit, right? And we get it for L length, so we try all the lengths here. And it turns out that if I ran this, yeah, oh yeah, this is right. So yeah. If it's 1 digit, you have 9. If it's 2 digits, 37. Up all the way up to 9 digits, it's 3026. Maybe should it be 10? Maybe it's 10. I don't know. Maybe it's 10. Or roughly 10. I don't know. Why don't I print that actually? Didn't I write this out? That's actually confusing. Why doesn't that? Oh, I guess it just ran out of space for this from the last one. That's why. Okay, that is just silly on my part. Okay, let's see. Yeah, so as you can see, 10, you know, it's not that big of a deal, right? Yeah, I don't know. Do I need 10 digits? 10 to the 9 only has 9 digits. Why do people keep on telling me 10? I don't know. Because a lot of people are giving me comment on that number, but I think they're just wrong. In any case, as you can see, if this is either 4,000 or 3,000, it doesn't really matter, because if this is 4,000, then let's go back to here, I guess. If this is now 4,000, then you can see that it's 4,000 times 10 times 100, which is, I guess, 4 million, which is still not great, but it should be fast enough. One thing that I would say, and looking at the submission time, which one is this? Can't be over number. So 791, this is actually quite fast, so I'm not really worried about it. But honestly, this can actually be even optimized more, because we do the number of digits left, and so as a result, we can actually put this outside each core. I'll bring the comment with it. Because this is the same across different problems, and actually even this is and even this is the same across different problems. And technically this is a prefix sum that you can also cache, but we don't need to, so we're not going to. But yeah, so I mean, even this, I guess we don't really need, but so this should work, right? And then we can submit it. Then you can see that this feels faster. How much is it faster? Well, not fast enough that Leetcode will load, but yeah, it goes from 791 to 38. So you went way faster, right? But yeah, that's all I have for this one. Let me know what you think. And yeah, I mean, I'll go over it again really quickly. Yeah, so for L digits, we just calculate the sum of all the small digits, and this is how you do it. But the key part is this function where you keep track of the total, the product, and the left. And honestly, this function should be easy to write. It's very standard dynamic programming at this point in the Leetcode thing. So I'm not going to go over it. That's why I didn't go over that deeply. I think this part is a little bit harder to kind of come up with precisely. You have to be a bit careful, but I don't think it's that bad. It's just keeping track of the prefix. And honestly, maybe this PP and PS is a little bit confusing. You don't even need to write it this way, right? You could just, maybe if you are a little bit worried, then you can just say, like you could just add another loop, right? Because we have 10 numbers, so if you want to add a factor of 10 is fine. So then just like for J, right? So then now for I in range of, I don't know if it's J or J inclusive.
right? You can just pre-calculate it. I think that's a little bit easier to understand anyway, but you can think of it this way as the previous numbers, right? And this is I, and that should give you exactly the same thing, right? Well, if I didn't mess up some paren things, yep. Oh, well, now you have to do the entire thing again. I think that's why, but yeah. Oops. Nope. But yeah, I mean, it just, but I think it makes it slightly understandable. I don't know. Let me know in the comments. But again, like, I don't really worry about what is going on. Oh, this is J. Right? Yeah. I mean, it's basically the same, right? Now you separate out. This is basically the give all the prefix, and this is just one digit at a time, and then you just keep track of the prefix, right? As we said, and getting rid of, and then sum up all the digits or at one at a time. And yeah, that's all I have for this one. Let me know what you think. Thanks for watching, and yeah, you could watch me solve it live during the contest next. 5170. I mean, okay, doing so good so far. Even if there's so many technical difficulties. Anyway, we have 2 positive integers, L and R. Beautiful. If the product of the digits is divisible by the sum of the digits. Count. Okay, 10 to the 9. The product of its digit is divisible by the sum of its digit. It goes up to 10 to the 9. I mean, the inclusive part is just easy to change, but how do I just count in general? Okay. So by definition, 1 digit is going to work, right? 2, 10 is going to be 11 is not, 12 is also true. Oh no, product of its digits. So actually 12 is not. Is 10 true? The product of the digits is 0, right? Oh, I guess 0 is divisible by anything. Well, okay. So the thing is that it's always going to be so given how do I think about this? So given all of them are this for 2 sets of digits, they're all are gonna be true, right? So okay, well, sum of the digits. Huh. Alright, I mean, what I want to do is actually start out by trying, yeah, if trying something, I don't know. Print I, right? Just want to see what it looks like for the first 1,000 numbers before. Okay, S is 0, S cannot be 0, so whatever, start from number 1. Huh, it's okay, so is this like a SIF problem? But no, it goes up pretty high, right? So I don't know. Okay, so any number with a 0 in it has it. That's fine. That's every 10, right? Just because the sum is 0, or the product is 0. The product here is 20. The sum is 10. Oops. Oh, because it's 2 different cases. How many numbers is that? 1 to 100. Okay, so every 10, that means that it's going to be at least 100. But then after that, how many is there? Right. $333. That's just 1/3 of them, huh? But it's not evenly distributed per se. Oh, and it's more than that. It's just all the numbers of, because of the stuff like that. As long as it's not leading, then yeah. So how many numbers don't have a 0? Let's see, and so 153 is still a lot. Do I know anything about these? 1 digit. I mean, I knew that the permutations are working, but okay. I don't know. Ten to the 9. What does it mean? I don't know that I know this one, or what this one means so far. Okay, what's 195? So 45 over 15. Is this a 6-pointer? Oh, people got it very fast actually. But maybe just cheaters. Dare I try a little bit more? They are every 3. Why are they every 3? I mean, they're not every 3, but if we are able to check every 3, that'd be nice too. But can I build smaller pieces? Oh, jeez. Can I combine two 2-digit numbers? It doesn't seem like it. I don't have any idea. I mean, and I'm skipping out the zeros because that's just trivial, right? I don't know. We have to count them, but it's trivial to count in theory once we get everything else out. Well, maybe not. I don't know. Either way, we still. Is it just digit DP? How would digit DP work? Yeah, I guess it's just digit DP. Why am I overthinking this? I don't know. I don't know if it works honestly, but it makes sense to me. The f of r minus f of l minus 1. I think that's it, right? And then def f, we have x. Okay. Okay, yeah, I'm just thinking about for it. Okay, so L is equal to, this is the number of digits, and then what? I'm always a little bit rusty about digit DP. I don't practice it that much, and nowadays I don't practice anything anymore. But okay. You can't do a for loop on everything, right? What would the digit DP look like? Is the digit DP like? Because you do have to keep all that state, and I don't know that it's easy to do all that state. Let's try. I don't know if it is, but we can try. Okay, so okay, let's try it for the first digit, right? So yeah, okay, so the first digit, so Sx of I, right? Is the first digit. That means going up to it, we want all inclusive, right? So here we might try that's wrong actually. No, that's the first digit. What am I doing? Okay, it's for I in Sx of 0. Okay, so this is the first digit, and then now we want to calculate the, okay, so the sum is going to be just I, and the product is going to be also I technically, but we want to skip the prefix. I think that's the problem with the prefix zeros. So, okay, so we can just brute force this, right? Okay, fine. For L in range of L, so that's for the length, right? So return calc of L, maybe calc total. So this will give me gets the count for all numbers of length L, right? And then yeah, okay. So that assumes that the first digit is not 0. Then we can do for I in range of the first digit, it's going to be from 1 to 9 inclusive, right? So then now that is just going to be go from I, and then we have L minus 1 left, right? So okay, so total is equal to 0. Total, we add this, and then we return total, and we're good, right? And then we have go, we have the total, we have the product, and we have left, number of digits left. This is complete. Gets the count for all numbers of length left to go, right? So if left is equal to 0, then we go if total is mod the other way around, I think actually. Yeah, okay, whoops. Product mod total is equal to 0, return 1. Otherwise, we do stuff, and we should cache this. Total and product should be very not that big, so that's I don't know. I don't know how to analyze this actually. Well, total can only be 10 digits, so it's going to be only up to 100. Product, I guess, if it's 99999 or something, right? I guess it could be 9 to the 9. That's actually pretty big, right? Can I do this better on the product side? I don't know, honestly. I don't know how to handle that. Maybe this isn't the right way to do it. But let's see. I don't know. Maybe there's something we can do to optimize. Okay. Otherwise, then now the next digit is going to be from 1. Actually, it could be from 0 to 9 now, and then that's actually a little bit awkward. Whatever. So we want to say total plus I and product times I, and then left minus 1. I mean, I guess if product is equal to 0, then we could get it, but that gets cached anyway, so I think that's fine. Right, so if product is equal to 0, then yeah, maybe we can update this, the base case. Then we turn 10 to the left power, right? So because we have 1 digit left, then it's going to be 10. Yeah, okay, I think that's fine. Okay. How do I feel about this? I don't know. Right, so, okay, so here we have total is equal to 0. Okay, so then now we have to do the prefix thing, right? So for the first digit, we go from 1 to 10 again. So the first digit, not from 10 to, what is it? Int of x of 0, right? So 1 to that, not inclusively. Then total we add to, actually just go of total I left minus 1 or L minus 1. I think that's actually okay. But then now we have to recursively go right, and then calc total, right? I think this is a calc total anyway, but yeah, I think this is wrong. I don't know if it's wrong, but it. Oh no, it's not a calc total because it starts off at 0. So okay, so I think this is fine. I mean, it gets memorized anyway, I think. Otherwise, otherwise we go to the next digit. So I think there's like a 4J in range from L here. We go to J. So the prefix is equal to 0. But the prefix product is going to be 1. Prefix sum is going to be 0. So then, yeah, it does this thing, which is this product, PP times this, and PS times this. Or the other way around, whoops, PS plus this. And it's not L, it's L minus J minus 1. And then when we go to the next digit, then P. And PP is fixed, right? Then PP we times it by int of x of j. Something like this. I mean, I should return stuff. That would be, oh no, I return. Max depth, in which one? Always go left by 1. Line 20. We still left -1, so why is that wrong? Okay. I mean, this seemed okay. Well, that's already wrong, but I was gonna say that looks pretty good, but maybe not. I mean, this is just whatever it goes 13. Why does it think it's 13? I don't have the mental energy for this. I don't even know if this is right. Let's actually run it for like, I don't know if it's fast enough. I think that's my problem. We'll see. In my test case, okay, it has to go up to. Actually, that is fast enough. That is actually surprising. Then, okay, maybe I'll give it a think. I thought it might not be fast enough, but if it's fast enough, then I could think about it. Okay. I mean, it's wrong, but, you know, it's fine, maybe. Okay, we can probably play around with... okay, so maybe I'll just do a loop, honestly, for I in range of 15 or 16, from 1 to 16. I f sub I, right? Okay, so one is should be 1, so I think we already messed up there. But it seems like we just why is 1 0 not work? Oh, because I don't so maybe I'm off by 1 somewhere, but that's fine. Maybe it's not great though. 10 should be good, but 11 is not, right? Which is refracted. 12 divided by 2 is... No, 12 divided by 3 is fine. Do I misunderstand this? Oh no, it's 2 divided by 3. I always forget. 2 divided by 3 is not right, so this is not right. Why is 1 wrong? 1, 2. I could see why it's wrong though, because here doesn't do anything, here doesn't do anything because length is 1. So okay, so it takes this 0th element. Oh, I don't check the actual number itself, I think. Okay, so that's why. Actually, then here, if pp ps is 0 to 0, total increment by 1. I think that should fix that, but yeah, okay. Well, ps is going to be 0. Why? Oh wait, this isn't right actually. This should be outside, so that's actually very awkward. P sum cannot be 0, right? Why could it be 0? That's actually weird. I mean, we do actually have a 0, but why? Oh, because the input is 0. Okay, fine. I mean, we can just, I don't know, if x is equal to 0, we just return 0. I think it's fine. Okay. I mean, it's not the... What? Okay, so here, I mean, this is still... No, this is right, I guess, because that's a 0. But 11 is 9 is very wrong. Right, okay, so... 2 and 9, okay. Oh. Actually, no, it's mostly right, but it's missing by one number. I don't know which one, though. Because if these are 10, it's actually accurate. Because none of these numbers are right. I'm off by 1. So 10, what is 10? 10, we do the calculated total, so okay. So that means that we should be doing calculated total on the first one. Should be 1. Oh. Oh, I know. Because of the rest of the digits, it should be 0. That's why. Okay, so that's why this is so awkward. If start is equal to 1, if j is equal to 0, start is equal to 0. That's pretty awkward though, but it's fine maybe. Actually, it's the other way around, I think, actually. Okay, so this looks good, but is it fast enough? I think that's the part that I don't know. I mean, it looks fast enough. Is it right enough? I don't know anymore. 2 and 10 is right? Okay. I don't know the answer, so I can't check, but I just want to check the speed, and that is obviously going to be the worst case. Click submit. Yes, okay. Oh, click my timer. Stop. Okay. So this one took me 26 minutes. Yeah. And the funny thing is that I didn't get any wrong answers except for Q1, which is actually embarrassing. But it took 40 minutes. So how? Okay, if Leetcode wants to load, that would be nice. How long would it be if Leetcode didn't suck? What would be my rank? So it thinks that, oh, actually it fixed it. Huh, so I lied. Okay, so Leetcode did sometime fix it, so I don't need my sketchy notepad thing. And I think the timing is roughly right. It matches my thing by within 5 seconds, which I was just messing around anyway. So I guess it figured it out. Alright, not bad. Let me take a screenshot for whatever. So okay, I mean, so we don't have to actually use this crappy edit pad thing. But I did have 2 wrong answers. So I would have been 109th, which, including all the cheating, is actually pretty nice. But actually, I don't know, because this one's for Q4, I was a little bit YOLO, to be honest, because I don't know I couldn't prove the complexity on this because of this product. Like the numbers can be big, and I know that not all the numbers are possible, right? So how would you put the bound on this as a thing? Total can only go up to what's it, 9 times 9 digits or something, but let's just say even 100 for a thing. Product is actually what is product? Okay, well, with 1 digit it's going to be 9, right? Let's see. I think this is the hard part of the problem. Everything else, I mean, I was slow, but fine. 2 digits, it's going to be the number of, so it's not 9 times 9 because they're not unique, right? Well, it's 9 times 9 divided by 2 for 2 digits, I think. I don't think there's any difference. But after 3 digits, it gets... after 3 digits, it gets become like... it's like an n choose 3 type thing, right? So then, yeah, okay. So then it is... So after... So 3 digit... Okay, so... 1 digit is going to have 9, right? 9 possibility. 2 digits is going to be have, if we want to go for it, then it's going to be
It's not 9. Well, okay, so we can break it down by one unique digit, which is 9 choose 1 times 9 plus 9 choose 2 times is that it? No, wait. Am I thinking this right? Okay. 9 choose 1 times 9? Where does that come from? I'm gonna 9 choose 2 sounds right. Man, my math is terrible. I think this is right though. Because you have 9 choose 2, right? Because they can be every 2 digits and they're distinct, right? And then it gets a little bit harder. Well, I mean, if it didn't already. Which is then now you have 9 choose 1, then you also have 9 versions of these, right? And no, you don't have to. That's why I'm confused. Okay, so you don't choose times 9 because 9 choose 1 is the 9. You have 9 digit, and then you have 9 choose 2. But this part is the tricky part because now you have 2 digits in 3 things, right? So then now, and the only way to do that is pass 2 to 1, right? The it's going to be, what's it called? Yeah, 2 1. That's the only way. And then there's 2 ways to do that for each pair, right? So I guess it's just this times 2 maybe. Yeah, because you choose I think that's right. Plus 9 choose 3. And then I think that is a 111, so that's right. So I think this number is just the number of what's it called? Like a what's it, integer division of, I forget what it's called. Like distribution of integers something. Right. Like in this case, 9 choose 1, it can only be a part like if you think about it as like a visualization, then you can only have one thing of 3, right? Or one number, or 3 of one number. Sorry, the other way around. 3 of one number. Here it has 2 of one number, 1 of one number, or the other number. So that's why you have times 2, because it could be backwards. Maybe, I don't even know. I mean, I think for me, the actual number, maybe it matters, but it also doesn't matter. I just want to get like an upper bound kind of thing. So multiply by 2 is not that interesting for now anyway. Maybe we could do on that, and then we just have yeah, one way for 3 numbers. Maybe that's the way to do it, because it has to be 111, and then it gets obviously even more crazy. But 9 choose 1 plus 9 choose 2. 9 choose 2 now is tricky, right? Because then now it has yeah, I think it is just the number of ways to unique, because then now it's 2 plus 2 or 1 plus 3, right? I forget what it's called, but actually, this is actually just now that I see it, this is actually just 4 times I mean, the way that I did this is 2. So if you're going to rewrite this is actually like a 2 and 1. I write as 2 plus 1, or 1 plus 2, or 2 plus 1. But as a result, you have n minus 1 of these, right? At least for n. So here, this is times 3, because you have 1 plus 3, 2 plus 2, and 3 plus 1. It still gets trickier though, because 9 choose 3 is different as well, because then the combination is going to be 1 plus 1 plus 2. I guess that's it, actually, right? I mean, there's 3 ways to distribute the 2, but that's the only way, so maybe this times 3. And then if it actually looks, and maybe I'm very silly here, but you can maybe see the Pascal's triangle, right? Which is kind of just like a ridiculous thing that I don't know that I expected to see, right? Because then now, and maybe you should expect, because then now every number that's here, it is just adding 1 to here or here, right? And then as a result, that's how you get Pascal's triangle, which is also a ridiculous thing. Also, and here, or every possibility here, it's just from 1, 1, 1, or one of these and getting here, right? So it's I don't know if the math is quite right, but I think you see a Pascal's triangle thing. But that also means but there is this prefix, right? So it's not quite that, but oh, people in the comments are saying it is stars and bars. Unique product is based on factorization again to the math. Distribution link of all to the exponent set. Yeah, I'm just trying to find an upper bound for 9-digit, right? My intuition would say that it's not so bad, but I don't know. I'm just bad at math. I mean, that's the thing. It's not quite stars and bars, right? Though some parts of it you can think of it that way. Or maybe it is. Maybe my math is just bad, which would definitely be true. Oh, I guess it is actually. You're right. Okay. But then it's the summation of all the things, right? Does that sum to anything? Because basically this is saying that the star and bars make sense, because then now you have five things, right? So you could have 1, 5, and then you're happy with no distribution, and then plus the number of ways to have 1 bar. I guess 1 bar has to be in the middle. So then that is, so another way to think about that then, right, is this is, I mean, you have to yeah, I think that's fine. I think the 9 choose 1 thing is confusing. I think if you take away the numbers on these, so we can still do the numbers, and the bar is the number of ways, because given here, then now this is just 5 factorial with 1 factor over 4 factorial or something, right? So then it's still hard, but I think maybe there's an upper bound as a result. I don't know. Right, because okay, so let's say you have 9 digits, right? Then it is just you have 9 things, which is going to be just what 9 choose 0, right, or whatever. Or yeah, well in this case it's 9 choose 0. But and times 9, because each of the stars can be any number, and then for each contiguous. No, I mean I get that. I get how to use it. It's just that like the concepts is not what I'm having trouble with, right? It's actually plugging it in. Or rather, I'm trying to find a limit, right? And for me, it's not clear. Like we can do the math and calculate this out, and that's fine. And in fact, what we should do is probably write code to generate that, right? But I guess what I'm more interested in is not necessarily that, but it's that in the future, if I see a similar pattern, I would know that like for example, if we don't have to multiply by whatever, and you have just a summation of all these things, and then you know that this is basically Pascal's triangle thing without the multiply, like without the digits, then this is just Pascal's triangle, and then you know that the nth row of Pascal's triangle, the summation of that is 2 to the 9, right, on the 9th row. And that allows me to kind of be like, okay, I'm confident. I know that's gonna be 2 to the 9. That's good, right? For me, the issue is that with this extra complication, I don't know the upper bound to do it. Yeah, I don't know the right way to think about this in terms of like my what I'm trying to figure out is that for future contests, for future problem solving, if I have a similar thing, is like, but maybe the digit is not 9, maybe the digit is 12. Do I know what the upper bound is? And will I have enough confidence to implement it, thinking like before solving for it, have confidence that it won't time out before I implement it, right? So I think that's what I'm trying to solve for. And maybe we could figure it out. I mean, it's not that hard. Like, this is actually a fun, interesting problem to solve as well as a dynamic programming problem, right? It's not, but yeah, and we can actually, I don't know, is there, I feel like we can probably actually write that out really quickly too, right? Let's see. We could write that out really quickly in terms of the number of unique products that can come up with X digits, right? So maybe we can write another one as an upsolve. We can write what this is, right? So here we have digits left. So we have left, and then the current product, right? So we can just write it. Like if we really want to write if we want to know the exact number, we can. It's just that I wanted an intuitive thing, right? So here is the first digit, right? Yeah. Yeah, I mean, I think that's fine, right? So here, maybe we'll just cache it so that we don't even have to cache it. We just have seen as it goes. No, I mean, we should cache it because why not? And then here, the first digit, we just go from 1 to 9, right? And then maybe we have for L in range from, let's just go from 1 digit to 9 digits. So again, right, so here we want to say the first digit is going to be L minus 1, right? Yeah, and then maybe we set total is equal to here. We add this. We don't even. No. We don't need to. We have a scene array. We calculate this, and then we just print out the length of scene, right? And then here we go. If left is equal to 0, then scene dot add p, right? Otherwise, then we just for I in range from here we can go from 0 to 9 or 0 to 10, right? Or well, 0 to 9, but you know what I mean. We could go to p times I left minus 1, right? And that's it, really. We should return, and then now we should be able to see L and scene, right? So we can write that code really quickly, right? Scene is equal to z of 0. Did I have a 0 somewhere? Whoops, I just typed it in for some reason. I don't know. Okay. Go to text 2. Oh yeah. How did? Oh, I think I was just writing it thinking of the other one. Okay. Yeah. So one digit has 9. Huh. That doesn't feel right though, right? Am I doing this wrong? This feels small. Or am I wrong? I mean, let's take a look real quick, right? So with one digit, 1, 2, 3, 4, 5, 6, 7, 9. With 2 digits, a lot of them is going to be 0. So that's 10 is going to be like 5 times 2, 6 times 2, so 2 times stuff, 3 times some stuff, 4 times. So maybe there's only 1,000 possible numbers. I mean, we do all this math, and it's just that the number of unique numbers is 1,000, right? So I think that's basically the key for this one. It turns out is that product. There are only 1,000 unique products, which I find fascinating and surprising. We do all the math, and we just had to write like 5 minutes worth of code, and we're Gucci. So I don't know. You got? Am I wrong? I mean, I know that it's going to be a lot. Obviously, it's going to be a lot less than 9 to the 9, because if that's not the case, this would obviously time out. But it's just, it's not about knowing. It's about like an order of magnitude, so that you can, at least for me, right, figuring out in the future. But I don't know if I'm doing it wrong. If I mean, there's only 1,000 unique things, but that's a lot fewer than whatever you're saying, right? Because this, well, the thing is that this also dedupes, like for example, 18 is 2 times 9, but also 3 times 6 for 2-digit, right? So this is actually going to be smaller number than doing it this way, because you dedupe on that, so it makes it even more fewer dupes or more dupes, right? And I guess as a result, there's just a lot of things like that, because 2 times 9 is equal to 3 times 6, so the product, like the number of unique products is even smaller, and it turns out there's only 1,000 unique products, which is a very round number, by the way. So that's also a little bit wonky, if you ask me. Is that even, how can that, this also doesn't, oh no, okay. So, okay, I see. So this is not the prefix sum. This is just 1,000 numbers of exactly 9 digits. So I didn't prefix that. So in that case, we could just take this out, and then we could get the prefix number, and maybe that's what you're saying. Yeah, okay, but still only 3,000 though. So maybe there's some dedupings there. I don't know what is. Yeah. No, it's still not available during the contest, because I guess we're still technically in contest. But yeah. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this contest and this problem, this explanation, everything in between. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye-bye.